it's been pretty amazing to be kind of at the forefront, at the cutting edge, to see all the luminaries in the field, and you find out that these big names are just people with a lot of common interests that overlap with yours, and who will only be too happy to talk with you about them.
Hello, everyone. This is C++ modules getting started today. First, a quick introduction, just so you know what kind of talk to expect. So this is meant to be an introductory talk for people who have never used modules before, don't really know much about the feature yet. The goal is really to help you get enough knowledge so that you can start trying out modules on your own, start playing around with it, and get familiar with the feature for the first time. You will not learn everything that you need to know about modules here. I'm going to simplify a few things. I'm going to leave out a few things. The goal is really to provide you with enough knowledge that you can get started and focus on the things that are most important, that give you the most value. In particular, I'm going to focus on the things that already work well today in the tools that are available. We're not going to cover some of the more advanced features or features which implementations don't support well. I submitted this talk because I wanted people to have a good introductory talk, a good first talk that you can watch. There's already lots of excellent second talks out there that you can watch, and you should do so. Some of them I will reference in this talk. Some of them you can see at this conference later, so I encourage you to deepen your knowledge. So this is me. I'm one of the co-organizers of the Munich C++ user group. We're always looking for new speakers, so if you're interested in getting into speaking, feel free to approach either me or Klaus Igelberger, who is one of my co-organizers, who is also at this conference. So let's dive in with a familiar example. This is just your classical interface implementation split that you know from header files and CPP files. We put the declarations in the header file, and then the implementation, in this case, the function definition, goes into the CPP file. And now if a client wants to use this, they're just including the header file, and then they can call the function. So this should all be familiar to you. And of course, there are a few problems with this include style mechanism. So one thing that is not so nice here is that there's really no restriction on where you can put an include, right? So this is a particularly daunting example where I just interrupt the function definition in the middle and then pull in the function body from a header file. You may have seen code like this before. I've seen this done in production. So some people would claim this is even a useful feature. But you probably all agree that this can also lead to pretty horrible code. Another problem with include files is that they require include guards, right? This is something that we all got so used to that we don't question it much anymore. But if you think about this, if I forget the include guard, and I include the header twice, then it's pretty likely that I will end up with a redefinition error. And if you're like me, when you encountered this for the first time, this was probably a pretty confusing thing to you. So that's not nice. Another thing that is not nice is that the include files are not really isolated from the surrounding state, right? They're always interpreted in the context of the translation unit that includes them. So, for example, in this case, I have a class definition, and you might think, oh, this is a private function, so nobody will ever call this. But, of course, your translation unit could be particularly evil and just define private to public, and then they have access to this. So this is a particular pathological example, but it's actually quite common to have header files that rely on the surrounding state that is set up by the translation unit to change behavior. That is again something where some people might claim that's a useful feature, but it is also something that can lead to very brittle code. Somewhat related to this, include files don't really need to be self-contained. So in this case, I'm using std vector in my header file, but I forgot to include the vector header. This example will compile just fine, but if I now swap around the order of includes, it will break suddenly. And I guess most of you have encountered a problem like this, where changing the order of includes just breaks the code. And this is always super painful to debug. And yeah, really not nice if you encounter it. The last problem is a little bit different. That's a problem of build performance. So the include file, since it gets like textually pasted into every translation unit, that also means for every translation unit that gets compiled, I have to process the entire code of the header file again and again. So if I have two translation units that both pull in the same massive header, I have to process that code twice, which of course has an impact on my build times. So modules are here as a better alternative, and they will solve all of these problems, and it's a completely new mechanism. So let's take a look at how this works. So this is our simple hello world here. I'm just defining a single module that is just exporting a single file. So the first thing to notice here is this export declaration at the top. So that is really the signifier that tells to the compiler that this is a module file now. You may notice here I'm giving the name of the module here, in this case my_module, and that name is different than the file name that I use for the source file. This is different to how many other programming languages do this. In C++, those two names are actually independent. And if we look now at the client side, it uses this import statement to make the exported function available. And the import statement refers to the module by that same name that we used on the export side. It should be noted that these names that we give to the modules, they need to be unique across the program so that the compiler knows when we write import something, what module we're actually referring to. And it's the developer's responsibility to make sure that this uniqueness is respected. Another thing that's worth pointing out here is modules don't introduce a new namespace. So the module name is really only important for the import statement. It's of course good practice to put your stuff into a namespace if you're exporting it to the wider world. But it's not, you don't get an implicit namespace as part of the module here. So one important difference compared to headers is that we have to mark everything that we want to make available to our client explicitly with the export keyword. And there's a number of things that we can export. So the first thing is we can export functions. We can also export types. We can even export templates or function templates. And this might already be the first little surprise. So if you're a little bit like me, then you might be tempted when exporting a template to write the export on the second line. So after the template type name something, because that's usually the place where we put all of these various keywords that you might need to put on declarations in C++. The way that I like to think about this is what we're exporting here is really the name of the thing, right? So if you think about like what is actually being exported here, it's the name of the type, the name of the function. And the name is being introduced by a declaration, right? And the template type name something, that is part of the declaration, right? So the export goes in front of this because I'm exporting the full declaration. That is how I like to think about it and how I can remember this where it goes. We can also put the export in front of a namespace. That is a nice shortcut if you want to export just everything that is within that namespace. However, this export really only applies to like this particular block that you open the namespace in. So if I open the same namespace again later without the export keyword in front, then what is in there will not get exported. And that makes sense if you consider that a namespace can always be reopened at any place, right? And you wouldn't just want a single export in your entire code base to have a global effect on everything. Another thing is that you can put an export on a using declaration, like we see here at the bottom. This is particularly useful if you want to re-export things from components that are not under your control and that are not aware of modules yet. As usual with using declarations, that means you also export the thing from the namespace where you actually wrote the using in. So in this case, it will be exported from B. You will find that in the B namespace, right? So you have to write B : will be exported in B. But the exporting namespace can be the same as the one that you're using it from. What is new is that you can also have these export blocks. So this is, again, a shortcut. If you don't want to repeat the export on every single declaration, you can just put them all in an export block. But be careful that you don't have something in this block which does not make sense to be exported. So here I also have a static function in there. Static functions have internal linkage that does not really make sense to have that exported. So if you have something like this in there, you will probably end up with a compile error. So just be aware of that you separate your things like that. Then lastly, what you can also do is you can export entire modules. So here I have a module A, and then I have a module B, and then on the last line, you see this somewhat peculiarly looking export import. Sounds a bit silly, but really what it does is, so if you just do import, then that means I want to use everything that is in A. If I do export import, then that means I'm now also, as part of the module B, exporting everything that was in A. So to a client, if they just import my module, they also get everything that was in this module that I just export imported. One thing that you need to be aware of is that if you don't export something, that does not mean that it's completely unavailable. So in particular, stuff that is not exported is still reachable. Here we have an example of this. So the class not exported is not exported, but I export a function that uses this class as a return type. And now what the client can do is it can call this function, and it can actually use the struct, right? It can catch the struct return value, and it can even get to the member inside the I. What it cannot do is refer to that struct by name, because the name has not been exported, right? So if you try to catch this return value by the name not exported, the compiler will complain that it does not know this name. And this might seem a little weird, but really, if you think a bit about it, this is not really new behavior. So in particular, we have since C++17, I think, the auto return types, and there you can construct similar examples. Like in this case, what I'm returning is a value of a local struct type. And here we have the same situation, right? Where clients of this function are able to use this data type, but they don't know its name. They cannot refer to it by name. And in particular, you see this often used together with lambdas being returned from functions, right? Because with lambdas, you have this general problem that you cannot name this type. So there it's, if you've used code like this before, then that hopefully shouldn't be too daunting to you. Daniela Engert actually gave a talk about this 2 or 3 years ago, where she talks about what she called the 3 secret spices of modules. And she goes into great detail there about these 3 aspects of visibility, reachability, and linkage. So if you want to know more about this, you should definitely check this out. There's a lot of stuff in there that wasn't really that visible in the language in the pre-modules world, but that become really important now. So let's take a look at the different shapes of modules that we have available for structuring our code. So what we saw so far was an example like this, where I have the export module keyword, and then I just list all of the stuff that I want to export, and also stuff in there that I'm not exporting, but I put everything into a single file, right? And this is the one file that you always need to have. This is what is called the primary module interface unit, and that is what defines, like, under the name of my underscore module, what is actually the stuff that is available if I import this. So primary means you can only have one of these things, right? If you have 2, then you again have the problem that you have 2 things that declare the module of the same name. We don't want that. But you can actually put a lot of stuff in there. So like with header files, we had this inclination to always keep them really small, because otherwise your build performance gets pretty bad pretty quickly. With modules, you get a lot more leeway here. And I would even say, like, unless you have a good reason not to, feel free to just put a lot of stuff into this primary module interface, right? Like, try to put just everything in there and see what happens. And in many cases, it might already be good enough. So that would always be the default that you should try. First, just put everything into this primary module. But there's good reasons for splitting this and doing something more fine-grained. So the first thing that I want to show here is similar to the split that we have in the include world between headers and source files. We can also split our module into the interface and an implementation part. And so here we have the implementation part at the bottom. And we see the first difference is it does not have the export in front of the module, right? So it states which module it belongs to, but it does not say export. That's the difference between the interface and the implementation here. And then, because it's just an implementation, I cannot export anything from the implementation file, right? If I want to export something, it has to go in the interface. But it's enough if in the interface I just declare it, right? And then I can put the actual body of the function, in this case, just goes into the implementation. And I can have as many implementations as I want, right? I can have like a single primary module interface, and then have like as many implementation files as I want that contain the guts of it. And the advantage of this is, if you're again thinking about build times, if I make a change to the interface, then I not only need to recompile the interface, but I also need to recompile all of the clients, right? Because there might be something that has changed in the interface that affected them. If I make a change to the implementation, I just need to recompile the implementation and nothing else, right? Because since I cannot export anything, I cannot change anything in the implementation that would require clients to recompile. So that's a really powerful mechanism to like keep your the build times, in particular for incremental builds, at bay. Going one step further, you can also split up the actual interface into multiple parts. So this is what interface partitions are for. So here I have a single module mice, and I split the interface into 2 different parts. So I have one interface partition called Pinky, the other is called the brain. They all export different functions. And in the primary module interface, I need to export, import all of my partitions. And again, this is the developer's responsibility, is actually required. If you have multiple partitions, then the primary interface is required to export, import all of these partitions. So you need to be a bit careful here that you don't mess this up. The partition is internal to the module only, right? So somebody who just imports mice, they cannot tell which partition something comes from, right? So this is purely for structuring the internal structure of your module implementation. One thing is that things that are inside these partitions, they're visible to the rest of the enclosing module. So in particular, I have a data type in here which is not exported, but that data type, even though it's declared in the partition of the brain, it is available for use for everybody inside the module mice, but not to the clients because it's not exported. One interesting question is now, what happens if I give Pinky also a secret master plan? So if I declare a type of the same name also in the other partition, because then the problem arises that one level further up at the module level in mice, I now have two types of the same name. And the nice thing here is that the standard actually requires that the implementation needs to check whether the two are actually the same. So you can have those two declarations, but if they don't match, if they actually declare different types, then the compiler needs to catch this. So Clang already implements this. It's pretty cool. You get a nice error message that tells you where the two types differ. In MSVC, this is currently not implemented. If you build this in MSVC, it just picks one depending on the order of the import statements. But that will probably be fixed before long. Right. So one thing to note here is that once you introduce partitions, you get a lot of corner cases like this, and things get a lot more complicated than they were before. So I would encourage you to not do this unless you actually have a good reason for split stuff, right? Just don't try to make it too fine-grained. Try to stick with just one primary interface, and only split this up if you run into a problem, if you actually see a good reason for doing the split. There's a thing called header units. I'm not going to talk about this today. If you want to know more, there's an excellent talk by Daniel Rousseau who explains not only what they are, but in particular also why they're a little bit difficult to implement and why it's probably not a good idea to try to use them in production today. There's still a bunch of unresolved questions around this. Daniel's take on this is probably a bit too pessimistic. Other people might be slightly more optimistic than he is, but he gives a good overview of what the problems are that people are currently discussing here. If you want to know more about like some of the other types of modules that I'm not mentioning here, watch pretty much any of Daniela Engert's talk. She has a bunch of really great talks about modules, and in pretty much all of her talks, she has this nice table which gives a good overview of all the different types of modules and what you can and can't do here. So really check this out. I took this screenshot from her latest talk at NDC Tech Town just a couple of weeks ago. All right, let's switch gears a little bit and talk about building modules. So the build system was the thing that has held back modules adoption for a long time now. And a lot of people have not really understood why that is the case and what is so difficult about this. So I want to spend a little time on talking about this. So let's start with an example that is just like old school, doesn't use modules at all, right? So in the old school world, I'm going to use CMake here as our little build system. You hopefully have all seen code like this. So I just have an executable, it has some sources, it has some headers. I list the header files here as part of the sources, but this is really not required. This is mostly to keep the IDE happy so that it knows like which header files belong to the project. But really the thing that is important is this line down here, which tells you what your include directories are, right? And then all of the files that are in this directory, the compiler can find them usually, right? So there's also like more stricter ways of like people that want more hermetic builds where you have to list everything explicitly. But in CMake, usually it's like, yeah, if you forget one of the header files, it will probably compile anyway. So the first thing that I want to tell about here is that like, this is really the old school way. If you're on a newer version of CMake that is like version 3.23 or later, we now actually have a new mechanism for this, which is file sets. And the way that it works with file sets is I use this syntax where I list the header files in their own section as the header files. I give the include directory not in a separate command, but I give it here as the argument to the base directories. And this is really nice because you can now specify everything as part of the target sources command. And it also makes, if you, for example, have a library where you have an install step also for the packaging later on, this is also much more convenient with the file sets. So if you're on a newer version of CMake, I really encourage you to adopt this. It's really superior in every way to the old approach. So why do I tell you about file set? Well, because that's the same mechanism that we also use for modules. So if you want to use modules, you use the same mechanism, only that now it's not file set headers, but it's file set modules. You can still give the base directories. They're not as important yet as they are for headers. You can also leave them off and it probably will still compile. But we now list all of our module source files down there under this set. To make this work today, you need a bit of additional magic. I really don't want to say too much about this because it's kind of arcane and not very interesting. If you're watching this on YouTube, then hopefully you are far enough into the future that you can ignore all of this. If not, there's a short link here to a Stack Overflow answer that I will try to keep up to date with all the incantations that you have to do in the latest version of CMake to make this work. Bill told me yesterday that probably in version 3.29, all of this will go away and it will become official. For now, you still have to do some magic stuff. It's here for reference, but really check the Stack Overflow answer. That has the latest magic in there. One thing that is really important if you want to try this is use the absolute latest tools that you can. So use the absolute latest version of CMake that you can. Make sure your Visual Studio is up to date. Have a really up-to-date version of Ninja. So with CMake, you need either MS Build, so build like within Visual Studio, or use Ninja for building. None of the other generators are supported at the moment. For Clang, it claims that it works with 16, but 16 has a bunch of horrible bugs in there. So really, you should be at least at 17. If you can, be at trunk. So there's like, even the jump to trunk is worth it. With GCC also, you need the absolute latest stuff. Bill just told me yesterday that module support was finally merged into GCC very recently. It now also has the dependency scanning mechanism, although the dependency scanning support is not merged into CMake yet as of this speaking. Hopefully, if you're watching on YouTube, that will already work also. Be aware, it's all still pretty new in all of these tools. You will find bugs in there. You will find inconsistent behavior. So yeah, take this like with the right mindset. But really, it's now at a maturity grade where I would encourage all of you to actually try this out and start playing around with it. Now is actually the time, if you find this even remotely interesting, to get your feet wet here. So a few things that I wanted to mention here since they come up early. When is a file a module source file and when is it a regular source file, right? When do I put it into this modules file set? You might be tempted to think, and that was my first intuition as well when trying this out, then whenever there's something in there that's related to modules, it goes into the modules file set. That is not how it works, right? In particular, if you're just importing modules, you're just a normal source file, right? The rule of thumb here should be, if you have an export module somewhere in your file, then it goes into the module section. Also, if you're writing an interface partition, whether it's an interface partition or an implementation, it goes into the module. In all of the other cases, it's just a regular source file. And if you mess this up, you will probably get a compile error. So this is the rule of thumb here. Somewhat related to this, there's some confusion about which file extension to use. When modules started appearing in compilers, we also saw a bunch of new file extensions pop up. And there was the question like, which of these should we use? So compilers have now more or less converged. They're like MSVC and Clang, I think, recognize all of these. GCC is more like, we don't care what your file extension is. Just give us anything and give us the correct flags and it should work. And if you're using CMake, then the file extension actually should not matter. So I'm using just .cpp for all of my examples here. And if you don't feel super strongly about it, I would encourage you to also just stick with CPP. There's no need to introduce a new file extension. Like tools often get confused if you use the new extensions, if they don't know about them yet. So yeah, just save you the pain. One thing to keep in mind though, if you do decide to use them, make sure that you really only use these new file extensions for a module source file. So take the checklist from above. If you try to use this file extension on a regular source file, your compiler might apply the wrong build mode, and then again, your stuff will not compile. So just keep this in mind. Okay, now, so let's talk a little bit about build systems. Like what is a build system anyway, and why is it so important here? So we probably all started out like this, right? You don't need a build system. You can just use the command line to build, right? And that will work, right? So why all this fuss? So what a build system really is in the end is a dependency tracker, right? So if I have a source file here, and it includes a bunch of header files, then the problem that I really want to solve is if any of these files changes, the source needs to recompile. And I want to track these dependencies, right? Because, of course, I could recompile all of the sources all the time, but that means that my build is not very efficient. What is worse is if I don't recognize one of these dependencies and I change, for example, one of the header files, and I don't recompile all of the sources that were affected by this, I end up with an inconsistent program state. And debugging stuff like this is really fun. So that's really why I want to build system, right? So that if I change any file in my build, then it automatically rebuilds like just the minimum set of files that were affected by this. It detects all of those files automatically, but it really does it the most efficient way and not compile anything more than necessary. So in the traditional build model for C++, like every source file can be compiled independently from the others, right? So here, all of the blue boxes represent source files, the green boxes represent header files. Every source file has its own dependency tree, but there's no interdependency between the different source files, right? And this is also like how build systems these days work, right? If you want to do a parallel build, it can just embarrassingly parallel invoke the compiler on all the source files, and there's nothing to keep in mind there. It can just figure out all of the stuff for each source file independently. So there's still the question, how does the compiler actually figure out which sources to rebuild if I change one of these header files? Because if you remember, like in the CMake file, I did not actually give this information, right? I did not associate the header files to any source files. So I did not even need to give the header files to make a build. So if you look at the command line that your compiler is using, then like for example for GCC, you might notice that it uses this -M flag. And what this does, it will write out this dependency file that tells you exactly this, right? It will tell you for the source file that you're compiling, what are actually all of the sources that it depends on, including all of the headers that you have included and transitively included. So if you think of the compiler, really what it does, if you think of it as like a processing step in a pipeline, it takes a bunch of source files and header files as inputs, right? So the source file, that's the one that I give explicitly on the command line, and then it implicitly pulls in all of the header file that it includes. Then it produces as an output an object file. That is the file that then will be also used by the linker in the subsequent build stages. And it will write out this dependency file that we see at the bottom as a byproduct of the build, right? So when I say byproduct, I mean this is not something that is actually needed to finish building the binary. This is produced to help the build system out to figure out what the dependencies are and how to do the incremental build. Right? This is really simple in very general terms what the job of the build system is in a header-based build. So what changes now if we switch to modules? So the big difference is now that instead of depending on header files, I'm depending on source files, right? Because all of the modules, they're source files themselves that get compiled also. So what does this mean for the compiler? So the output now is not just an object file, but it's an object file and then this file which is called the binary module interface or BMI file, which contains all of the information of like what is, if I'm compiling a module, what is my interface, right? What is the stuff that I'm exporting as a module? I need to write that out also, and that's a separate thing next to the object file. And unlike the dependency file, this is not a byproduct, right? This is not just to keep the build system happy. But if I have other source files that import this module, then those BMI files are actually inputs to the compilation of that source file, right? That's the big difference now, right? That I have some of the outputs of the compiler are inputs to the compilation of other source files. And the implication of that are, whereas before we could build each of the source files independently, we now have dependencies from, like between the source files, from one source file to the BMI that is produced by the compilation of another source file. And in order to produce a correct build, I have to build all of these blue source files in the correct order so that all of their dependencies are already available when I try to build them. That is the major difference in like how the build system works in a pre-modules and in a modules world. And this fundamental change in like that I now have these interdependencies between the source file, that is the main challenge in making sure that you can build with modules. And that is what we have been waiting for, right? There's actually a pretty good paper that I have in the references towards the end from the CMake implementers, where they explain in a lot of detail how they did this implementation for the Fortran modules. The C++ modules implementation is very similar to this. So if you want to understand this in more detail, I highly recommend that paper. It's really good. So what changes for the build system now? If we look at the the file set, we still just give a flat set of modules, right? We don't want to specify what all of the interdependencies are. We don't want to specify the full build graph, right? If you want to do this manually, then you can probably make any build files be able to compile modules. But if you want to just give the flat list and have the build system figure out what the interdependencies are, that's when it gets difficult, right? And this is what CMake gives you in its module support. So the question is now really, if one of these files changes, how can the build system figure this out? So for the header dependencies, which we still have, you can still have includes in the modules world, it's the same as before. But for figuring out these interdependencies between the blue boxes, the build system now actually needs to run twice. You need to do a first pass where you look at all of the source files and figure out what are they actually exporting and importing in terms of modules. So this is not a full compilation, but the compiler needs to touch every file once and figure out like what are the exports and imports. After that, you know what all of the interdependencies between the blue boxes are, and only then you can actually start the build proper. And then you can only parallelize up to what the dependencies allow here. So this is the big difference now. So if you try out a modules build for the first time and you wonder why every source file turns up twice in the build log, this is what is happening here. So if we touch this header in the middle, what that means is that we can leave the branch on the very left alone. This is not affected by the change, but I need to compile the middle branch, and I need to recompile also the right branch, which depends on it. And I can only start compilation of the right branch once the middle has finished because of the dependency. And this is like in really simplified terms, this is what the build system has to do. This is the difficult stuff to figure out. So if you wonder, like, why does my favorite build system not support modules yet, and will it ever support it? This is what it needs to figure out, right? So if you want to maybe submit a patch to your favorite build system, think about how to solve this. All right. As the last section to this talk, I wanted to give some useful advice for, like, if you want to start out using modules, what are some of the typical problems that you can run in, and what are like some of the like simple tricks to get around like some of the most common pitfalls that people run into. So this is just now a collection of advice that I hope will be useful to you if you start using this. So the first thing is, so usually the big problem with modules comes when you try to use third-party code, right? If you write everything from scratch, you just write everything in modules from the beginning, and everything that we've seen so far will be perfectly fine. So things become more interesting if you have to rely on code that is not under your control, in particular, like the standard library. So if you're lucky, you already have a C++23 compliant implementation, and that will provide a modularized standard library for you, and then again, everything is good. But what if you're not there yet? What if you actually need to use the standard library the old-fashioned way by including a header? So you would write it like this, and this introduces a new concept that I haven't been talking about, and that is the global module fragment. So you will notice that our export module declaration, which we had at the top before, is now actually in the middle, and at the top we just say module semicolon, right? And if you write it like this, then everything that is between the two blue lines, that is the global module fragment, and that is the section of your code where you can actually include headers. And the way to think about this here is everything from the global module fragment will be made available to use inside the module implementation, but it will not get exported to your clients, right? So you can, it's pretty safe to put headers in there. You can just use them in the implementation as you want. But if you pull in something there through the includes that you want to make available to your clients, then you have to look out. So yeah, all of the stuff between those red lines is part of the global module fragment. And all of the things that come below the export module, that is what is called the model purview. And everything that you want to export has to go there, right? You cannot export stuff from the global module fragment. So where things get a bit problematic is now if you come into the situation where you're mixing headers and modules. So let's say we start out with an example like this. We can have the modularized standard library. We export a function that returns a std string. So in this case, I can can just use this function. I can use the string. That is all fine. If I now try to catch the string by name and not by auto, I have the problem that main.cpp did not import the standard library. The module also only imported the standard library, did not import it. So the name stood string has not been exported by this module, right? So this will not compile because it does not know the name stood string. So you might think, now, okay, I can just solve this. I can just include string, right? And that will make the name available to the main.cpp. And this is actually where things might break for you. The problem here is that when you export a name from a module, you export it in the context of that module, right? So if you think about like what the mangled name of the thing will be, it will have the name of the module in there, right? When you get something from the header, that name is part of the global namespace, right? So it will not be attached to any module. If you now write it like this, then the stood string that you see up in the my module comes from the std module. So the name is associated to the std module. Whereas the name std string that we use down there in main.cpp is not attached to a module. And now if you mix the two, things will break. The guideline here is you should always put the includes first. Always, like, first include everything that you need and then start importing the stuff. And if you follow this guideline, then at least for the standard library, the standard guarantees that it will be able to resolve the names correctly. And if you're lucky, your implementation might even be able to do this for your own library. The state that we have right now, this doesn't work even for the standard library very well everywhere. So my advice for now would be try this, but don't be surprised if it doesn't work. The best practice today is really to keep those two worlds separate, right? So you have to decide globally for your project, do I want to refer to this name as the module name or as the non-module name that comes from the header? And you have to keep those separate, right? So if in the same translation unit you end up in the situation where there could be a confusion where the name comes from, you're asking for trouble. So in particular for the standard library, this probably means that if you have some code that is not under your control, you probably want to stick to headers for now. So let's say we have the situation that we export something that depends on the standard library, right? So this is a pattern that you might be tempted to use. So I have a library that works in terms of headers, and now I want to modularize this. And I don't want to rewrite all of the complete header. I just want to say, like, everything that is in the header, I want to export it, right? I want to make this available under the module interface. And now you have exactly this problem that because you do the include string in lib.hpp, it will try to export everything that is in the string header as part of your module, and that will probably break. So one thing that you can do here is you include the header explicitly in the global module fragment. And what will happen here is when you're compiling the libm.cpp, in the global module fragment, it will include string. That will set the include guard for string. So then when you, in the export block, hit the second include string from the lib.hpp header, it will not do anything because the include guard has already been triggered and it will not be processed a second time. So this is a really useful trick that, like, within the context of like a single compilation, even if you're compiling a module, it will respect the preprocessor state. It will respect include guards. And yeah, this is not a way that you're probably used to think of, but like for modules, this is a really useful trick to keep in mind. Another thing that I want to mention is there's this possibility to export stuff with through using, so exporting using declarations. So if you want to, so again, we have this situation where we have a complete library header lib.hpp, and I just want to export a single symbol from this. And notice I have still the same typo that I wanted to fix after giving this talk last week. It actually should say export using on the last line, right? Apologies for that. So if I just say export using awesome type, that means like awesome type from the letter lib.hpp. That's the thing that I want to export. There might be other stuff in there, but some of that might not be exportable, or I don't want to export it. But this way you can like pick and choose which parts of the header you actually want to make part of your module interface. One gotcha to be aware of, though, you will want to fully qualify the types if you're using this export using syntax. So that is also a little gotcha here. And then the last thing that I want to mention is, so one of the things that is really nice about modules is that they don't export the preprocessor state to the clients. This is really nice on the one hand because it gets rid of a lot of the problems that we saw in the beginning. But it's not so nice if you actually have something in a legacy library that actually relies on the preprocessor, and now you need to make that available to the clients. So how can we do this, right? So the macro, there's no way to export that, right? Our clients won't see that. So one way to solve this is to just say I always strip a header along with my modules, right? So I put all of the stuff that does not require the preprocessor, I put in the module, and then I have a hopefully really small header file next to this, which provides all of the preprocessor stuff. That's a simple solution here. A much cleaner solution is to invest a little bit more work and actually expose the preprocessor related stuff in a form that does not rely on the preprocessor. This requires some refactoring, but you could, for example, instead of using macros for numerical constants, you could use nice const expr variables, and maybe you can maybe you will find a replacement for some of the more complicated macros as well. This is not always possible, but yeah, if you can do this, then this will probably lead to a much cleaner interface. One disadvantage of this is of course that client code now also has to change and needs to be adapted to this new C++ified interface. You probably won't find a way that reuses the same identifiers that the preprocessor used before and make that compile. Daniela gave a keynote at this very conference last year where she showed a couple of examples for different types of libraries, C libraries, C++ libraries, like very, very different interfaces, and how to modularize those. In the talk itself, she didn't go into a lot of details, but I highly encourage you to check out the GitHub repo for this talk, which contains the entire source code. She's still maintaining this and updates it frequently. And that's actually a really good, reference to check out some of those techniques for dealing with different kinds of interfaces and how to modularize this. So wrapping up, modules are slowly maturing. I would claim that at this point, they're really mature enough that you can try them out. And you should try them out today because they're a really cool feature. And yeah, it really pays off familiarizing yourself with them. There's still a lot of dark corners, right? Implementations are still buggy, but the more people use them and discover those bugs and report them, the quicker those get fixed. So it's really something that is worth looking at right now and help improving this feature. The main challenge that you will face is probably integrating legacy header-based code. That requires a little bit of knowledge that you didn't know before. There's a bunch of new tricks to learn here. But it's also interesting practices, and you might learn a few things about the language that you didn't know before. I want to really stress this last point. So right now, if you start playing around with this, you will notice that a lot of stuff that is quite simple does not quite work as expected yet. This can be a bit frustrating because you run into roadblocks really quickly, but there's also a chance in this. Because that means there's a lot of really low-hanging fruit in the compiler implementations, in the tooling, that can be addressed. So if you always wanted to get started in contributing to an open source build system or a compiler, there's pretty good stuff in there. You can really make an impact here. Also, if you're interested in writing a tool that makes builds analyzable, for example, right? There's a lot of really cool stuff that is new, that was newly introduced with modules that can be leveraged here, which does not require a lot of work, but just nobody has bothered so far to write those tools. So yeah, if you're looking for an interesting topic to make a contribution to the community, to get involved here, check this out. There's a lot of great stuff there. There's a lot of potential that can get solved, and you don't need crazy amount of time investment to get started here. So really, this is one of the main messages that I want to get across. If you're interested in doing this, now is the time, and you can really make a change here. I have a few references here. In particular, there's a talk right after this by Lewis over there in the Cottonwood room, which talks a bit about the challenges of packaging and binary distribution, which I didn't talk about at all. Definitely check this out. All of the talks by Daniela are great. Check out her stuff. Check out what she has on her GitHub. Lots to learn there. Bill gave a great talk about the state of modules in CMake. If you want to know more about this, check out his. And I also gave a bunch of things that you can read if you don't like to watch talks. Yeah, and with that, thank you for your attention. And we have some time for questions. If people want to ask questions, please queue up at the microphones. Yeah, let's get started.
First of all, thank you for the talk.
Sure.
I had a question about the templates. Classic gotcha with header-based building is that you need to define the whole templated class in the header file.
Yeah.
How does that work with modules?
Yeah. So the question is about the fact that with headers you cannot really split the implementation of the template into the source file, right? It all has to be in the header file. This is still true for modules. So the problem is that the site that instantiates the template still has to know all of the inner details in order to carry out the implementation. You can only hide that away if you already know what all of the types are that this template is going to be instantiated with. So in that regard, nothing really changed compared to the include world.
So that's kind of the follow-up question is then, how does that tie into your tip with keeping everything in one file? Something like std vector, std string, these are quite big templated classes. Yeah. Is this one of the cases where you would split it into these partitions?
So you're worried about build performance here, or?
Not just the code size. I would have a file of 200,000 lines.
Yeah. So one thing to keep in mind here is that 200,000 lines in header files are a very different story from 200,000 lines in a module file. So if you look at Daniela's keynote from last year, she actually put the entire standard library into a single module and then measured the build times, and it was super fast. And that was I think 150,000 lines of code something. And there was really no reason, just in terms of build times, to split this up. So if you're not worrying about incremental build performance, when you make changes to the standard library implementation itself, if you're just worried about rebuild performance for your clients, there's no reason to split this up. So the modules are that fast, which is pretty great.
Okay, thank you.
All right, then let's take one over here.
I guess my question is pretty similar. You mentioned you have to do an export-import for basically every partition that you do in the module file. I was wondering, like, I assume that means users can't import just a specific partition of a module?
Right, yeah, that is correct. So the partitioning that's purely internal to the module, the client doesn't know anything about the partition, and they also cannot choose to just pull in the one partition. Yeah, that's correct. All right, then over here.
Hey, I've got a question about the name mangling.
Name mangling, yeah.
Yeah, so actually two questions, but the first one is it specified? You said that if you included a header and then import std, then the compiler should work it out.
Yeah.
Is it specified in the standard that that's supposed to be the case for your own libraries too?
I think, so as far as I know, it's only specified for the standard library. It's not guaranteed to work for anything else.
Okay. And the other question is, why would there be anything mangled differently at all in modules? Do you know that? Yeah,
so check out Daniela's talk about linkage. She goes into more detail about this. I fear it's a little bit too complicated to answer here on stage, but yeah, her talk, she explains that pretty well.
Okay. Yeah. I'm also kind of unclear on why it would sometimes work for your own libraries if it's not specified.
Complicated reasons. It's, yeah, I really hope that at one point we will understand the mechanisms well enough that we can just mandate in the standard that will work for everything. But I think at this point, it's still too early to give a definite answer here. It's quite complex what is going on there, and it's, yeah, it's a gray area at the moment.
Okay, thanks.
Sure, yeah.
So actually, tied the same theme. So what are the current plans for moving the standard libraries into module? I mean, is there something you can expect to see, kind of what's the timeline?
What is the timeline for that to be available? So on the Microsoft compiler, it's already available. If you compile in C++23 mode, it's supported. There's still a few bugs in there. So it's like I showed, like if you mix the import and include, it doesn't quite work yet in all the cases on Microsoft. I don't know what the status is on Clang. And I mean, GCC just got the module support, so they're quite far from that. So yeah, it might take a while before that's widely available. You can do your own. I mean, Daniela basically wrote her own modularized standard library. That is possible. It's a bit of a challenge, right? You have to be up for it, but it can be done, right? So there's not really anything that is stopping it, right? It's just somebody needs to do the work.
So in Microsoft on 23, you don't need to have includes anymore for any STD stuff.
Exactly. Like if you don't have any components like legacy components that rely on it, you can just do everything with import STD and Bob's your uncle. It will just work. Yeah.
Thank you.
Sure. All right. Then please.
I have a couple of questions.
Yeah.
First is regarding the partitioning of modules. So you mentioned that if there is some declaration in one partition, it's available to other partitions as well.
Yeah.
So won't that lead to a initialization order problem? For example, if there is something that's declared in one partition, it's used in second partition, but the first thing uses something else that's declared later in the first partition. Like
so that's an interesting question. So the initialization order situation actually got improved with modules. A lot of the stuff that was not defined before is now defined. So I think like that in most situations, you can probably write it in a way that it will work and it will work reliably. But it's an interesting question and it's very complex. It's too complex for me to like give you a definite answer that like if there's still some problems left. But yeah, it's definitely an interesting problem. I know that in a lot of cases it won't be a problem, but I don't know if there's still some difficult cases left where it could still be a problem. Yeah.
I have a second question. So
sure.
We saw that in the headers case, if there are different translations units, like they are trivially parallelizable. But that leads to a dependency ordering in case of modules. So like we have benchmarks on how the compilation times get affected between.
So your question is whether the build times might get worse because of this dependency. That's an interesting question. So of course you can set up like a pathological case where your build is completely linearized. And then, it will probably not be nice. If you're thinking about like what is the typical case that you can expect, you have this trade-off that because of the dependencies, you lose some parallelization, but the individual build steps are still much faster because you can just process the imports faster than you could the include. And usually, like the expectation is that it will be faster overall. In particular, if you're talking about incremental rebuilds, then the expectation should be it will probably be a lot faster than it was before. But yeah, in the end, it depends a lot on what your code size looks like. And I think there's a lot of potential for like analyzing and optimizing dependencies in this way. At the moment, we don't have a lot of tools for this, but this is like one of the low-hanging fruits that I mentioned. So all of these dependencies, how they're communicated to the build system, that is all specified, that is all standardized, right? So this is standardized file formats that are used there. And I guess you could write pretty quickly a tool that actually analyzed the builds and like pointed out where you have particularly long dependency chains that might be problematic for build performance. But yeah, this is definitely a new problem to look out for that we didn't have before.
Thank you for the talk.
All right, thank you, yeah. Please.
Hi, thank you for the talk. I just
Sure.
wanted to know if it probably depends on the implementation, but do modules work or are they expected to work with precompiled headers?
Are they supposed to work with precompiled headers? So the motivation was really for them to be a replacement mechanism for precompiled headers.
Yeah, well,
I actually have not tried to use them because I mean, yeah, I can still have includes in the modules, right? So there would still be a use case for them to use two mechanisms at once. I actually haven't tried this, so I don't know, to be honest. I wouldn't be surprised if it doesn't work since it's supposed to be a replacement, but yeah, I don't know. Feel free to try it out. And,
I tried a few months ago and it wasn't. But
it wasn't
I
working.
never
Okay.
researched if it was like a bug or something.
Yeah.
But okay, thank you.
Okay, yeah, sure. Thanks. Then last question over here.
Thanks. So thanks for the talk, first of all. You mentioned the module name should be unique. Now, we know other languages have these notations with dots. You know, it's .com.
The inverse DNS that Java uses, for
like
example.
Right.
Yeah.
So do we have any guideline in C++ on hierarchical modules?
Yeah. So one thing that we specifically get for the module names that we don't have for any other identifiers is that you can use the dot, right? So it doesn't have any special significance. It's just a character like anything else, but you can use that as a structuring mechanism. We don't have agreement on a convention like we have in Java with the inverse DNS, but you're completely right. The fact that this name has to be like unique across the whole project means that we probably want something like this. Because if you think about like all of the libraries will be modularized someday, then you either need like a global registry where you can check like which names are still available, or you need a naming convention like this that is sufficiently unlikely to produce name collisions. And yeah, this is something that we don't have an agreement on yet, but it's a very real problem. Yeah.
Thank you.
Thank you, Ben. Thank you all.